So we'll continue from yesterday, and as I said, one of the experiments that's useful because it doesn't depend on chemical exchange broadening measures the transverse relaxation interference constant. Now this is called eta xy, and it is the difference between the width of the two doublet components in an IS spin system. So this is run most commonly for the N15 amide group in proteins. So we have the doublet that's split by the JNH coupling, and then one of the lines is narrow, the other line is broad because of the Troisi effect, but they're both broadened equally by chemical exchange. So the difference between the two line widths is independent of chemical exchange. It's not usually the case that the measurement is made by measuring the two line widths. Usually one does one of two things. One would be to measure the decay of the narrow line of the Troisi line and the decay of the anti-Troisi line, and then take the difference between the two. But the other approach that's more common is to measure the interconversion between in-phase magnetization and antiphase magnetization, because that difference is, or antiphase magnetization can be thought of as the difference between the two doublet components. Right? If we have okay, so I've done something with the eraser.
Can you use that little piece of cloth?
Probably.
Or the eraser itself with?
And if we have in-phase magnetization, the two doublet components have the same integrated intensity. They may not be the same height because they'll have different line widths, but they have the same integrated intensity. And antiphase magnetization looks like that. So the amount of antiphase magnetization is the difference between the two doublet components. So if we started, for example, with in-phase magnetization, the amount of antiphase magnetization is 0. But if this line relaxes faster than this line, a little while later, we have this situation in which now the integrated areas are different. So the sum of the two is proportional to the in-phase magnetization, and the difference between the two is proportional to the antiphase. So depending on our viewpoint, right, this would be, for example, I alpha SX magnetization, and this one would be I beta SX magnetization, as an example of some operator that we would use to describe each doublet component. Right? This is transverse S magnetization, whose coupling partner is in the beta state. This is transverse X magnetization of the S spin, whose partner is in the beta state, or the alpha state. If we sum the two of these, we just get SX, right? Because I alpha plus I beta is equal to the identity operator. So the sum of the two is in-phase magnetization. The difference of the two would be SX I alpha minus I beta. And that's equal to, if I divide by 2 and multiply by 2 2SX IZ, the antiphase operator. So I can then think of the cross-relaxation effect, or the relaxation interference effect, as differential decay of the two doublet components, or I can think of it as cross relaxation between the in-phase operator and the antiphase operator. And they're both equivalent, but most of the time we make the measurement then by thinking of cross relaxation. So what the idea is going to be is in this first block, it's actually done backwards from what I just said. In this first block, we generate antiphase magnetization, allow it to relax, and then this part here is, along with this pulse on hydrogens, select then either antiphase magnetization or in-phase magnetization for detection. So due to the cross relaxation, if we start with antiphase, we'll end up with a mixture of antiphase and in-phase magnetization because of the phenomenon shown on the board. So in one experiment, we'll purge the in-phase magnetization and detect the antiphase magnetization. And in the second experiment, we'll purge the antiphase magnetization and detect the in-phase magnetization. So now we have both components. And then it will turn out, if we do the mathematics, that the ratio of those two intensities builds up as a hyperbolic tangent. So then this fitted curve is the hyperbolic tangent for these two, and here is then the rate constant measured for ubiquitin. Now, if we want to use this for comparison for detecting chemical exchange, then we need an experiment to measure R2 in which chemical exchange isn't suppressed. And this can be done in lots of different ways. And here's just one way. This is, right, two spin echoes, one cycle of a CPMG experiment, but Waltz decoupling is turned on in each of those blocks. Waltz decoupling is turned on to make sure that the magnetization stays in phase. The spin echo is going to refocus the J coupling, but during capital T, during this period capital T over 4, the J coupling is going to evolve and then be refocused, and then evolve, and then be refocused. And as you'll see in a moment, that will perturb the measurement of R2. If we're just using the CPMG to try to measure R2 directly, we usually make tau CP as short as we can, and then repeat the block over and over again, so that the J coupling has very little time to evolve. In this particular case, but as you know, if we pulse quickly, the chemical exchange broadening will be partially refocused. That's the whole point of the CPMG relaxation dispersion experiment. So here we want to measure as close to the full exchange contribution as we can, because we're trying to detect all the sites. So we don't want to pulse quickly. So we're just going to do this experiment with two values of T, 0 and some large number, so that we're not pulsing quickly. But if T is large, we're going to have a lot of evolution of the J coupling before it gets refocused. So to avoid that, Waltz decoupling is turned on during these periods, and that prevents the J coupling from evolving, so the magnetization is locked as in-phase magnetization. One has to worry then about imperfections introduced from the Waltz decoupling, so one has to pick a value of T over 4 so that an integral number of the Waltz cycles happen during that period. So Waltz is a very highly compensated decoupling sequence. It's highly compensated against B1 inhomogeneity, against resonance offset, but only if you have a full supercycle. So you can't have parts. So that limits the values of capital T. You have to be able to fit a full cycle of waltz into T over 4. Most of the time that's not a big problem. One just has to be aware of it. So then, this experiment, one measures an R2, and here's a graph of the R2 measured with this experiment versus the measurement of eta xy. And you can see there's a line, and then there's residues that are well off that line. And these then are identified as having an exchange broadening contribution. And if we plot the deviations from the line, then you see over here that there's some scatter around 0, and then some points that are well elevated above the line. One problem is, what does this scatter do to? So if you look back at what we talked about relaxation interference, the relaxation interference rate constant depends on delta sigma, the chemical shift anisotropy. And these data were analyzed using an average value for the chemical shift anisotropy. But of course that varies from site to site in a protein. Different backbone amide sites have somewhat different chemical shift anisotropies, and we usually don't know what they are. Experiments to try to determine individual site-resolved chemical shift anisotropies in solution aren't very precise, so one usually ends up deciding that the error in the data is probably bigger than the variation in the CSA value, so that hasn't been so useful. And there's relatively few proteins in which site-specific CSAs have been measured by solid-state NMR. So the smallest chemical exchange that one can detect by this experiment depends on the variation in the chemical shift anisotropy. So you can see that's more or less plus or minus 1 reciprocal seconds, which means you really need a chemical exchange broadening of probably at least 2 per second before you can reasonably detect it with this experiment. So that means there's always efforts to develop better ways of detecting small amounts of chemical exchange broadening that wouldn't necessarily depend on a parameter that we don't know so well, like the chemical shift anisotropy. But that leads into the problem of the CPMG experiment. And why is J-coupling evolution important? So when, let's see, I got to remember. So if we look at this pulse sequence, you can see that here's one CPMG cycle. It's done 2n times, so really one block is 2 spin echoes as always for the CPMG. And then there's this period U, and then another block of CPMG cycles. So the question is, why is this period U stuck in here? This wasn't in the experiment where we were using a CPMG just to measure R2, in which tau CP would just be as short as we could possibly make it. So let's think about the evolution of magnetization here, because now if tau CP is long, the J coupling will evolve. So we have in-phase magnetization, we have antiphase magnetization. To a good approximation, the antiphase magnetization is going to relax with R2 plus a contribution from the remote hydrogens interacting with the amide hydrogen. The amide hydrogen Z spin, Z operator, will be relaxing with due to R1 processes with all the other hydrogens in the vicinity. So that's just shown here by adding in a contribution from the remote spins. Now there could be cross-correlation effects, other more complicated effects that are being ignored here, but this is a 0th order approximation. And these are interconverted, of course, by the J coupling. So as the J coupling evolves, what we're interested in is relaxation of this in-phase operator. But depending on the length of T, we're going to generate some antiphase operator, and that will mix in some of this remote relaxation. Even if the J coupling is eventually refocused so that we come back to in-phase magnetization, the amount of in-phase magnetization that we end up with after a spin echo will depend on how much additional relaxation there was as the J coupling evolved, because that antiphase operator that was created and then refocused is relaxing faster than the in-phase operator is. We can make that effect smaller by deuterating, but we can't make it go away. And deuteration isn't as helpful as you think, in part because even if you deuterate to high level, when you put the protein back into water in order to protonate the amides, you also protonate all the hydroxyls and the side chain amide groups. And there's more of those than you usually think of. NMR people don't normally think about the serine hydroxyls, the threonine hydroxyls, the tyrosine hydroxyls, because you don't see them in the NMR spectrum. But they're there, and they're causing relaxation of any hydrogens that are around. So we can make the effect smaller, but we can't make it go away. And the problem then is, as we change tau CP, our goal in the dispersion experiment is to change tau CP so that when tau CP is small, we're pulsing faster than the kinetic jump rate. And when tau CP is long, we're pulsing more slowly. So we see a dispersion in the relaxation rates. But as we change tau CP, we're also going to change how much we mix in the contribution from the remote protons. So we'll have two effects going on. The effects on the dispersion curve from chemical exchange, and the effects on the dispersion curve just from evolution of the J coupling and introducing more or less remote hydrogen relaxation. So the problem is clear. The problem was clear enough that when I was a postdoc, I wrote a paper that said we could never use the CPMG experiment for studying chemical exchange in proteins because of this effect. So I set the field back for a decade, and this is just some arithmetic. At the end of that arithmetic, for one spin echo, we can then define, I guess I should say a little bit about the arithmetic. So let's call this matrix L. If I call this matrix L, I can integrate this differential equation, and I'll have an exponential, of course. So here is now, for one spin echo, if I start with in-phase magnetization, then it will evolve for a time period tau as this complex exponential, where L is the rate matrix. And then P is my spin echo. That represents the inversion. So that's just going to change the signs of the chemical shifts. And then we'll get evolution again. And then I'm going to read out just the in-phase magnetization. And then I can monkey around with the matrices, move this up to here. And now that just says I have the product of these two matrices. And that leads to the definition of an effective rate constant in the spin echo that says I have R2 plus a contribution from the remote hydrogens that depends on the J coupling and the length of the time period tau, as we expect, and it turns out to be a sinc, 1 minus a sinc function, if we go through and look at those matrix exponentials. So if tau is very short, the sinc function approaches 1. The sinc of 0 is 1. So if tau is short, this becomes 0 and we get the pure R2. But as tau becomes larger, the sinc function eventually approaches 0, and we mix in 1/2 of the remote R1 rate. And that makes sense because on average, if we have free precession, on average, half the time we have in-phase magnetization and half the time we have antiphase magnetization. So we would just end up with the numerical average of the two rate constants, which would just be R2 plus 1/2 of the R1. It turns out for a protonated protein, this remote R1 is about equal to the R2 of the nitrogen, so that this is about, in the limit, about a 50% addition, which is large. So that was the problem I pointed out a long time ago that said we should never do this experiment. But we were sitting around one day in the lab here at Columbia drinking coffee, and Pat Laurie and Chris Kroenke suddenly realized how to fix the problem. So the problem is, we started with in-phase magnetization. It gets partially converted into antiphase magnetization. And their idea was, well, let's just now swap in-phase and antiphase. So if we started with primarily in-phase here, or we started with in-phase, at the end of the spin echo, we're back to in-phase, but it's mixed in a little bit of the antiphase relaxation. Now let's turn that in-phase magnetization into antiphase magnetization. And then the next time period, it's going to be primarily antiphase magnetization, but mix in a little bit of the in-phase relaxation. So this is a matrix that does that just swaps in-phase and antiphase magnetization. We have to figure out a pulse sequence to do that eventually. But in the beginning, we just stick in this matrix, do the calculation, and then Mathematica will tell us that at least to first order in Taylor series expansion of all the exponentials, that process just gives us an effective rate that's R2 plus 1/2 the R1. It's no longer dependent on tau. It has the downside that we've made the rate constant larger, so the signal decays away a little more quickly, and we'll generally try to make that as small a problem as possible by deuterating, but we're no longer dependent on tau, and that's the key part. We can now vary tau to get the dispersion due to chemical exchange, but we no longer have a contribution from remote proton relaxation. Dennis Torsha told me when we published this paper, he couldn't believe that the answer was so simple, so he wrote a computer program to simulate the whole experiment to prove to himself that it would work. And my postdoc advisor called me up and said I should take back your letter of recommendation since you said this was impossible. So here is the idea. If we just plotted what happens with the sinc function, when our tau CP is 0, we just have R2, but then as we make tau CP larger, we mix in more relaxation, we have the sinc function, and eventually this is going to settle down to the green line, which is 1/2, adds in 1/2 of the proton R1, and then the averaging experiment just gives the green line, independent of tau CP. When we did this the first time around, we thought we needed more compensation, so in fact we did it twice. We had a block of CPMG pulses that U element, a block of CPMG pulses, another U element, so that we could get compensation to second order. But it turns out in practice that's hardly needed, and it just costs you more relaxation losses. So if you look in the first paper, we showed it with 2 blocks, but since then people have mostly just used 1 block. It turns out to our surprise, we didn't think about it, we only did this for the NHs, but it also works for, in addition to working for IS spin systems, it works for I2S spin systems and I3S spin systems. So now there are variants of this pulse sequence for amides, for methylene groups, for methyl groups, for NH3 groups at the end of lysines. And it's turned out to work a whole lot better than we would have thought in the beginning. So that's here was the pulse sequence. It turned out to be very simple to design an element U. It's just another inept period that takes then in phase to antiphase. And then the rest of this over here again is just an HSQC experiment to record the signal. Here is then the first data for BPTI. Again, fairly quickly, once we started to do the experiment, we got worried about these sorts of kinks. You can see here in these data, right? It's not really monotonic. We were used to monotonic kinds of decays. We were very worried about whether the experiment worked at long time scales. And then we realized that this was a signature that the system wasn't in fast exchange, that it was getting into intermediate to slow exchange. And then we realized that we needed a second magnetic field to have enough information content to actually fit a general expression for the dispersion curve. So now these experiments are always done in at least 2 fields, because again, delta omega increases with the size of the magnet, but the kinetic parameters don't care what size magnet you're in. And then we eventually realized actually that in the 60s, people knew there was this magnetic field dependence on exchange broadening, but they didn't really have any other magnets. So it's buried in papers and then was kind of forgotten about simply because of the limitations on magnets back in the 60s. One issue in these experiments is what's the limiting value? The limiting value here is R2 just from overall tumbling, the processes that are too fast to pulse out. And that's a fitting parameter generally. Depending on the decay, that might be more or less well determined by the data. So here, the plateau is pretty well determined here. It's perhaps not so well determined in a case like that. And that becomes a limitation in the experiment. And Christian Griesinger's group a few years ago proposed an experiment to measure the limiting value. The problem with getting to the limiting value is you have to make tau CP very short. And this is plotted as 1 over tau CP. So we need to make tau CP very short to get to the limiting value, but we can't do that. We generally try to keep the duty cycle at less than 10%, so that the length of the RF pulses are only 10% of the total time period during the CPMG. That's both for heating effects, but also the theory doesn't really take into account relaxation effects during the pulse. So if the pulse became a large fraction of the total time, we would have to worry in a serious way about relaxation effects during the pulse. During the pulse, you're going to have R1 row and R2 row like effects that will depend in complicated ways on the resonance offset of the spins. So that won't be so easy to do. And it's always been simplest then just to keep the duty cycle relatively short. But since the pulse lengths are of order 50 microseconds, that would mean that the minimum value of tau CP is on the order of half a millisecond, so that limits how far out on this curve one can get in order to define the plateau value. And the heroin experiment just simply says, let's replace the spin echo here with the CW field so that we're doing an R1 row experiment, and then turn the CW field on as strong as we can. And that turns out to be a very clever and simple way to get further out on the curve. So one can use that experiment to try to pin down what R2 naught is. But it's different from just doing an R1 row experiment because it still has this U period, so you're still averaging the in phase and antiphase. If we just did an R1 row experiment, we would always have in phase magnetization. We would never see this extra contribution from the remote hydrogens. Hans?
So, can you go one slide back? So on the CPMG curve.
Which way?
With the CPMG curve, where you show that. That, yes, right.
Mm-hmm.
So you pointed out that like at small tau CP, so to the right, that's hard because it gets too short at some point. And large tau CP are difficult maybe because the protein is large, relaxed for a long time. So it seems to me that the most like convenient data would be the data which are least useful. Is that right? So like the data between, in that case, for example, 0.4 and 0.8, is that true that those are easiest and easiest to get, or what would you say?
Well, anything between, I mean, one there is 1 millisecond tau CP, so one can probably get out, as I said, 0.5 milliseconds would get you out to 2. So out to 2 is pretty simple. And
so the higher the better, but not too high, basically.
As long as you don't get too high a duty cycle. Right, so the shorter tau CP, the better you define the plateau. The longer tau CP, the better you define where these kinks happen. So if we just had these data, it would be harder to decide what the fit was.
So, but it would be easier to get these data, right?
Yes.
So, but we couldn't use, because even without the, especially without the heroin experiment, we would, with these last 4 data points, it would be kind of, at this point in time at least, it would be not very useful, right?
But I don't know, for example, we've never tried, that if you left these points out, what would happen to the fit? I don't know.
Yeah.
So I don't know. I mean, it's quite clear we need at least a couple of points in here to know that these curves don't keep going up. But how much information there is here, whether you really need those or not, I don't know. We've never tested. Yep.
Does that mean for very large protein, the T2 is only a few milliseconds, that would be hard to...
That's right. So then when you go to larger proteins, which we'll come to eventually here, eventually we're going to want to do this experiment only on the TROSY line. So that rather than having in-phase and antiphase magnetization through here, we're only going to want to have the narrow TROSY line and then do TROSY detection. And that then gets one to larger proteins. That's been done on certainly up to 50 kilodaltons. But then, much larger, one has to switch over and do methyl experiments, right, in which one takes the advantage of the fact that there's a methyl TROSY effect and the methyl lines are very narrow. So at least up to 50 kilodaltons, these experiments will work on N15 if you switch over to the Trozy versions. But then, large things, it's really the methyl group, real experiments that Lewis's group has pioneered. Now, what do we get out of these experiments? In a good case, we're going to get K forward, K reverse, the populations, and delta omega. And delta omega we hope to use to get information about the structure of the other state. And if the populations are skewed, even if we're in slow exchange, we probably won't find that resonance directly. If we could find the resonance directly in the spectrum, we might just do ZZ exchange experiment on it. But remember, the line width of the minor state is proportional to the larger of the two rate constants, and the integrated intensity is proportional to the small population. So a 10% line, or 10% population, tends to be associated with a line whose integrated intensity is 10%, but its line width is increased by a factor of roughly 10. So these disappear very quickly from the spectrum. So we're trying to get information about the chemical shifts of the minor state out of this experiment so that we can then use those chemical shifts to obtain information about the structure of this alternative state. And here we did it back in the early days. We had 3 different models. We thought this was disulfide isomerization. We built some models of the different disulfide isomers. We looked in the database of chemical shifts in BMRV and saw that there was a large dependence on the nitrogen chemical shift depending on the rotamer of the chi-1 angle for a cysteine. And the different isomers had different chi-1 rotamers. Over here then, we just calculated from back then primitive chemical shift calculation programs. They've gotten much better. The calculated chemical shifts compared to the measured values, and there's at least qualitative agreement. These days this works much better, and Lewis's group has some really spectacular results. Notice one thing, however, and that's that I have the absolute value here. The equations for the CPMG experiment all end up depending on delta omega squared. So the CPMG experiment doesn't tell you the sign of delta omega, only its magnitude. So we're looking at some resonance. And we know the sign of delta omega, but that could mean that the invisible resonance was here or over here. And that's going to make a quite large difference in any kind of structure calculation. Sometimes we might be able to guess which is right by looking at distributions of chemical shifts. If this peak is already at the edge, the downfield edge of the distribution of shifts, then this probably isn't the right answer. But most of the time we don't know. And that's a downside to the CPMG experiment that is rectified some by the R1 row experiment. That's one reason the R1 row experiment has become more popular in recent years. But there are also ways of trying to estimate the sign of delta omega, and there's 2 ways of doing this. The first is to compare an HSQC experiment to an HMQC experiment. So to remind you of something from a long time ago, an HMQC experiment, the operator during T1 is something like And in an HSQC experiment, the operator during T1 is this. And if we think about chemical exchange broadening here depends on delta omega S. But this is a mixture of zero and double quantum coherence. So this is going to depend on delta omega I plus or minus delta omega S. And while we've talked primarily about broadening due to chemical exchange, there are also peak shifts due to chemical exchange, and you can see that in the simulations that we looked at last time. But then the shifts will depend differently, will be different in the HMQC experiment than the HSQC experiment. So a comparison of the peak positions in these two experiments can help decide what the sign of delta omega S is. The other approach is to take HSQC experiments at two different magnetic fields, and because delta omega S will depend on the field, the shift due to this chemical exchange effect, the shift in the resonance position will depend on the magnetic field. So one can make careful comparisons of HSQCs acquired at two fields and work out the sign of delta omega. Neither of these are perfect, but most of the time you can figure out that the sign of chemical shifts. And this is from a paper from Nikolai Skrinikov and came not quite a while ago. This is quite important because the sign, things can go very wrong if you don't know the sign of the shifts. And we once had a very good correlation between the absolute value of delta omegas for BPTI, the data that I've showed you, with the shift difference between BPTI free in solution and bound to chymotrypsin. So we of course thought we were looking at fluctuations in free BPTI to a minor state that looked like the bound conformation. But then we measured the signs of the chemical shifts, and once we had the signs, the correlation went completely away. So we were looking at something completely different than we thought, and we could never have known that without knowing the signs of the chemical shifts. Question? Yep?
Can that be an easy way to know is there some kind of exchange involved in this protein?
Sure. So that would be one way, one thing one might do in the beginning. Because there are regions of the parameter space where this effect isn't very large. People don't normally do that. The shifts are on an order of 1 or 2 hertz. So you have to very carefully reference the spectra, make absolutely sure if it's done on, if you do 2 different magnets, that the temperature is exactly the same. So one could do this in the beginning to try to decide if there was exchange, but it hasn't been used that way very much, I would say. But it could be. So then let's go to R1 row relaxation. Now the pulse sequence is basically the same, except we're going to replace the CPMG block with a spin lock. And the only difference between these two pulse sequence elements that would get stuck in here is how the magnetization gets aligned with the effective field. R1 row is the relaxation rate for the magnetization that's spin locked along the effective field. And the experiment, most of the time, not all, but most of the time, we want to get the magnetization to be aligned with that effective field. If we don't, if the magnetization, if this is the effective field and the magnetization is here, then there's one component that's locked And there's another component that's orthogonal to the effective field in the vector sum representation. The component that's orthogonal to the effective field is going to rotate around the effective field with a frequency omega e. Two things will happen. One, that magnetization component relaxes with R2 rho, which is usually much larger than R1 rho. So that component decays very quickly. In addition, B1 in homogeneity means that omega e isn't a fixed number. It varies due to the B1 in homogeneity. So there's additional dephasing because of B1 in homogeneity. So usually that orthogonal component decays away very fast, and it's just signal lost to us. So that makes the experiment inefficient. So usually we want to try to get as much of the magnetization aligned along the effective field. And one of the first hints that we didn't do that in some pulse sequence will be that we see a very fast initial decay followed by a slow decay of the magnetization. And that very fast initial decay will be the decay due to the B1 inhomogeneity and R2 rho processes until all that's left is the spin lock magnetization. And that's usually a warning. We have to go back and fix the pulse sequence somehow. But there's two strategies. One is to align by a series of pulses and delays to bring the magnetization to approximately the frame of the tilted frame. And then the other idea is to use an adiabatic sweep to bring the magnetization to the tilted frame. So an adiabatic sweep starts the R1, the B1 field at 0 and way off resonance, and gradually turns it on and sweeps into resonance or near resonance in such a way that the magnetization goes from Z to the tilted frame. And there are standard ways of doing that, and once we're at the right tilted frame, the magnetization is locked. You'll notice here there are two pulses, and this is to get rid of the cross-correlation effect. Again, will be cross-correlated relaxation. We usually want to get rid of that. So here there are two pulses to do it. Early on, it seemed like a good idea to do lots of pulses, just like in the R1 experiment, to do, say, pulses every 10 milliseconds or 11 milliseconds. So as capital T got longer, there'd be more and more pulses here. But that turned out to lead to some recoupling of the J evolution, so that then the data was artifactual because you had some evolution under the J coupling. Essentially, you had done a kind of solid state experiment in which we had recoupled in the tilted frame the scalar coupling Hamiltonian by the same mechanisms by which in solid state you would recouple the dipole Hamiltonian. So it turns out here it's okay if this field is relatively strong, then the recoupling effects of just having two pulses are quite weak. But over here, the RF is weaker, and now one has to worry about the recoupling effects, and the trick was to move the magnetization to the tilted frame, move it back to the z-axis, then apply the pulse followed by a gradient, go back to the tilted frame, back, tilted frame, so that the 180s were only applied when the magnetization was on the z-axis to keep the J coupling from evolving. It comes at a little bit of a cost because you have to move the magnetization around all the time. But if the RF field is weak, that's kind of the standard way of doing it now. You have to measure the B1 field strength, and there's a couple of ways of doing it. One easy way is to just do CW decoupling on the nitrogen during the acquisition period. And then you'll see a reduced J coupling. You won't see the full J coupling. The J coupling will be reduced. and it's reduced in a way that depends on resonance offset, the tilt angle. So we can measure the J couplings. We know the J coupling in the absence of the field. So tan theta is measured here. There's a straight line fit, and from the slope one can get the value of the B1 field. So that's more accurate than just measuring a 90-degree pulse. So in this experiment, we like to know the B1 field as best as possible. One can also do it using the pulse sequence itself, in which we do one experiment, T is set to 0. We do one experiment where A and B are both present, one experiment in which neither are present, and one experiment in which only A is present. And then those 3 experiments can be combined as shown here, and they turn out also to depend on theta. So one can do it both ways, and we've done it both ways. It really doesn't matter. This is the result of a nutation experiment. In a nutation experiment, we put the magnetization on Z, turn on the spin lock on X. For some time period, the magnetization starts to precess around the B1 field, and we then turn off the B1 field, apply a gradient so that we dephase the transverse magnetization, measure how much Z magnetization is left. And ideally, that should just follow, right, a sinusoidal dependence, but it's more complicated due to B1 inhomogeneity, because now you have the superposition of different sinusoidal dependences. And if we Fourier transform that, this then is an integrated distribution of the B1 field strength. And I hope you agree that's a pretty ugly looking profile. This is for a relatively old probe. You might imagine, in the ideal case, you would like to see a delta function, and at worst, you would like to see something, right, that looked maybe like a Gaussian, so that there was some uncertainty. And you can see we have a Gaussian here, followed by some big lump. Luckily, that's not a probe we use for these experiments anymore. We have better probes, but it also means that there's some possibility for trying to improve the analyses by taking into account the known distribution of B1 inhomogeneity on a given probe, and it's really not been done very much in these experiments. We just all pretend we have a B1 field that's a delta function and ignore the effect of B1 inhomogeneity when analyzing the data. So again, here's back to some data for BPTI. What's shown here is R1 row data as a function of omega E squared. And the different bars here, so this is using the adiabatic sweep and relatively strong B1 fields. This is using alignment with pulses and weaker B1 fields. These data in here are the CPMG experiment that you saw earlier, and then the curve is the result from the CPMG data. It's not a fit to those data points. It's just been calculated from the CPMG data to show that the R1 row data is very consistent with the CPMG data. The equations that we showed for R1 row, and remember, said that R1 row is sensitive to the offset from the minor species. So that if we made measurements at different RF offsets, different values of omega RF, we could find where the minor state was, because that would be a maximum in the R1 row rate constant. So here are 2 values. 0 is the observed peak. Here we made an R1 row measurement offset by a little less than 2 kilohertz to one side. and then we made the measurement offset by 2 kilohertz on the other side. In the fast exchange limit, these two measurements should be identical. Outside of fast exchange, the largest rate should occur when you're on resonance with the minor species. And the solid line then is the curve we expect based on where we knew from a variety of experiments what the minor frequency was. And you can, obviously I picked the points to make the point that, as expected, the maximum occurs where we expect the minor species to be, even though that's a completely empty part of the NMR spectrum. We can't see a peak there at all because that peak is only populated at 1%. So it's an integrated intensity of 1%, and it's almost 100 times broader than the main peak. So we just can't see it. And this turns out to be the main advantage of the R1 row experiment, is the ability to find where the minor resonance is. That's the same as knowing the sign of the chemical shift in the CPMG experiment, but it comes out for free here. One just has to collect data at different resonance frequencies across the spectrum. And that then led to the CEST and DEST family experiments. So now it turns out that suppose this peak got to be very broad, this curve, this black curve got to be very broad. If it got to be very broad, I would have a hard time telling the difference between one side and the other, right? And the width of this, it turns out to be a function of the kinetic parameters, but also the size of the B1 field. So there's an advantage of using weak B1 fields in order to make this curve as narrow as possible, and that increases your ability to find the minor peak. And Lewis Kay's group developed that very elegantly in what they called the CEST experiment. The name CEST actually came from imaging, an experiment developed by Peter Van Zyl in imaging that was called chemical exchange saturation transfer, and it links back to an experiment from the 60s or 70s called saturation transfer that was developed by Hoffman and Forschen. And the idea is, if you think of it as saturation transfer, we have two lines in the spectrum, a big line, and in this case some weak line. We don't even necessarily know where it is, but they're exchanging with each other. If we saturate this line, due to exchange, this resonance intensity will go down, right? Because the saturation gets transferred over. So we just have to put the RF carrier somewhere, turn it on for a while, and look and see whether this intensity has decreased. And since we don't want to directly saturate this line, the RF has to be very weak over here, right? Because if the RF is strong, it's going to also hit this peak, and we'll get saturation of this line even if there's no exchange. So we need a weak RF field, and if we don't know where this peak is, this minor peak is, we just walk our way through the spectrum, collecting spectra at different RF frequencies. And since we don't really care about measuring the rate directly, we can just use a fixed value of the irradiation time. We don't have to vary the irradiation time. We'll just fix capital T, record one spectrum, move the RF carrier, record another one. As it turns out, it's useful to do the whole process twice with different values of omega 1 of the B1 field, say 25 hertz and 50 hertz. Having that data is helpful. So here's the experiment. It looks just like the R1 row experiment, except we don't bother trying to align the magnetization along the effective field. This field is so weak that theta is very small if the field is weak, and that means in the time period capital T, the orthogonal magnetization is just going to relax away from R1 rho and the R2 rho and the B1 inhomogeneity, and if that's a very small amount of transverse magnetization, who cares? So we don't bother trying to align the magnetization. We just let the orthogonal magnetization dephase at the beginning of this period capital T. Then we just wait, measure the signal. In the original publications, since this was adapted from this MRI experiment, it is thought of as chemical exchange, saturation transfer chemical exchange. But it can equally well be thought of as an R1 rho experiment. We've turned on a field and we're watching relaxation. So these can be regarded either way. So the magnetization decay, if we think of it as R1 rho-like, we're going to have a decay due to R1 rho. And then a factor, turns out that there's a factor of cosine squared theta. The first factor of cosine squared theta comes because we don't bother aligning the magnetization initially. So the magnetization that's along the effective field is only goes as cosine theta. Some of it is dephased. And after the period capital T, we don't bother moving the magnetization back to the z-axis. This pulse, this gradient dephases the magnetization that's not along z. So we just read out the part that's along z rather than the total magnetization that's along the effective field. So we lose another factor of cosine theta. So we're reduced by cosine squared theta, but this theta is typically under 10 degrees or so, so that's not much of a loss. And then we just have R1 rho. So here's an example of the CEST-like experiment. There's a minor state here, the major state. Omega RF is marched along. And then when we get on resonance with the major state, with the minor state, the relaxation rate is enhanced and we see that dip. This is the intensity of the signal, so the intensity goes down. This is uninteresting. This is the major peak. Here all we're doing, we're on resonance with the major peak, all we're doing is saturating the major peak. So that's uninteresting. We're always reading out the intensity of the major peak. That's one thing that can be confusing about the experiment. We're never measuring the intensity of the major or the minor state. We're always measuring the intensity of the major state. But that intensity is perturbed when we're on resonance with the minor state. It's also perturbed when we're on resonance with the major state, but that's not interesting. We're just, at that point, directly saturating the major state. So there's the minor state. And black and red are numerical calculations and the R1 rho calculation, and they're indistinguishable. And I forget what the blue dashed line was. What does it say? Oh, this is just two different values of omega 1. Is that right? Well, it is down here. I don't know. I don't remember what it is up here. Now, this depends on the chemical shift difference between the two states. But you also could have a huge relaxation difference between the two states. Suppose you had a small peptide binding reversibly to a fibril. When the peptide is free in solution, its R2 might be quite small. But when it binds to the fibril, its R2 is just going to be enormous. Its R2 might be a microsecond, or T2 might be a microsecond at that point. We'll never see the CEST effect because the line is just too broad, so we won't actually see an effect on or where the chemical shift is, but there still will be saturation transfer effects, and that's shown here. And this is called DEST, for dark state exchange saturation transfer. The idea is the fibril is a dark state. Its line width is so broad we can never measure it. But whenever the peptide is on the protein, we'll then get saturation, or on the fibril, we'll then get saturation transfer. So it's the same effect. We are marching the frequency across the spectrum. And what we see is not a dip, but a change in the width of the profile for different irradiation frequencies. And this is due to the difference in the R2 values. So here I probably chose, I forget what I did, but probably picked 20 per second, same relaxation rate for the peptide, and then a huge relaxation rate for the peptide bound to the fibril or whatever. And again, here are the calculations. And these kind of data then tell us that there's exchange between the two. We can't get out the chemical shift between them. That's kind of lost in how wide these two curves are, or the one curve is. But we still can get information out about the kinetics. Long ago, a long time ago, Allerhand called the first case C-type exchange, where we're sensitive to the chemical shift difference between the states. And this bottom case he called R-type exchange, where we're sensitive to the relaxation rate difference between the two states. But that's language that's lost in history. People don't normally use that, even though it would be very useful language for describing these. But if you look in the literature, these are normally described as saturation. Actually, it's quite funny. In the solution NMR experiment, these, both CEST and DEST, are normally described as being saturation transfer experiments. You're irradiating a site, there's saturation transfer to the other site. If you go to the MRI literature, they're normally described as R1 row type experiments. So it's a little confusing. I discovered we were getting a lot of citations from people I didn't know at all, and they were in the MRI literature. This is to show the similarity between the two experiments. So here is an R1 row experiment in which we measure the relaxation rate constant as we step the RF field. And here's the identical system in which the CEST experiment is done. The RF frequency is shifted and the intensity is changed. And you can see here, when the relaxation rate goes up, the intensity goes down, as it has to, because the signal is relaxing away. And if we took the logarithm of this and inverted it, it would then look like this. Because of course we could always define a rate constant as the logarithm of the intensity ratio divided by capital T, the irradiation time. So which experiment to do in which case really depends on the parameters of the system. The CEST experiment is super easy, very convenient experiment, but it won't work if exchange starts to become too fast, and then the R1 row experiment has to be done. So one thing that's still a little unclear, and that in fact we're hoping with Bruce Johnson to generate, is software that would help, given some guesses about a system, which combination of experiments do you really want to do to optimally define what's going on with minimal amount of NMR time. Because otherwise, if you just say, I'm just going to do everything, one can burn through a whole lot of NMR time. Yep.
I think many people only wonder sometimes what is the most, like, experimentally, because you certainly. So, what is the most difficult thing about the R1 row? Why is it's like everybody will say it's so hard, but
Right.
nobody really knows. Says
So-
specifically what's so difficult, or what is the most difficult part? They just say everything is hard. So, what's the most, or the biggest
Oh.
mistake, or?
In the beginning, the CPMG experiment was hard, and then suddenly it became easy.
Yes.
And the R1 row experiment, I would say, in the hardest part, the trickiest part is making sure the magnetization is well aligned with the effective field and that there's no heating. So, you know, the pulse sequences have gotten better, spectrometers get better. I don't think there's any magic thing, but if I look back to the CPMG experiment, you know, after we thought it up, we had a terrible time making it work, and now it just works for everybody. And I don't know what along the way caused it to work better, other than just gradual accretion of better pulse. People got more, you know, pulse sequences improved somewhat, magnets got better, hardware got better, people got more practice using it. So I think it's just kind of evolution.
Maybe some type of protocol which just has to be circulated.
It's not so clear, but yeah. Here's a nice paper by Shi Zhang at UNC, in which he took an RNA system and on that same system did CEST, R1 row, and ZZ exchange. So this shows some of the CEST data. And then I think the next slide shows some of then the R1 row data on the same system. And then for a couple of peaks he was able to do ZZ exchange on the same system. So you can compare the three different methods, at least in that system. So I recommend that paper to you. That's certainly at this point the most comprehensive comparison. And then just to finish up, then what happens if we go to big proteins? So now here is the CPMG experiment. It looks the same, except this is a Trozy experiment from here on. And you can see this U period has an extra 180-degree pulse. So what's going on here? You'll remember that when we talked about Trozy, that I said the broad line and the narrow line were non-secular because of evolution under the J coupling. They kept, that evolution kept the two lines from cross-relaxing. If we start the pulse with a spin echo, the J coupling might not be evolving to where they become non-secular. Right? To become non-secular, we have to let the two operators kind of become anti-parallel to each other. But if we're pulsing quickly, they never dephase like that. So now the broad line and the narrow line start to cross-relax. They cross-relax with 1/2 of the remote proton R1. It's the same relaxation matrix, we're just thinking of it differently. And now what's the trick? If the two operators spend time like this, parallel to each other, then we want to, in some sense, make them anti-parallel to each other for some time. And I said that spins aren't very smart. We can trick them into thinking they're evolving relative to each other if we periodically invert them relative to each other. So if we start out with our broad line, and narrow line having the same phase, later on, we want to flip one of them so that if there's cross-relaxation going this way, then later on we want cross-relaxation going back that way to try to undo the effect. So this is a pulse sequence element that just does that. It flips one of the two doublet components. So if we have antiphase magnetization here. We'll have in-phase magnetization here. That looks exactly as the same before. It's just that we have to have this extra 180 there because we care whether we go from alpha to beta. So, right, one 180-degree pulse changes alpha to beta and beta to alpha. We don't want to do that because that's swapping broad and narrow lines. So we need two 180s to make sure we stay, alpha state stays alpha, beta state stays beta. So that's really the only difference in this experiment. It would have been harmless to put that pulse into the CPM, to the conventional CPMG experiment, but there was no need to, so we left it out. But here it's essential, otherwise we're swapping alpha and beta states, which we don't want to do in the Trosi experiment. Otherwise it's the same. Here is an example in triose phosphate isomerase, just some residue that doesn't have exchange broadening. So we're just measuring R2 in this experiment. And if we do the regular experiment, R2 is 41 per second. And now in the Trosi version, R2 drops to 20. So if we're trying to measure exchange broadening on top of that rate, obviously it's going to be a lot easier to measure exchange broadening riding on top of 20 per second than riding on top of 40 per second. And with 20 per second, we have more time to vary tau CP before the signal is all just decayed away from the relaxation processes that we don't care about. So that experiment works very well. So here's the purpose of U. Now we want to change the sign of one of the components. That's just the math. Just some recommendations that you can read. Here's some rough ideas about time scales, but these are kind of rough. I think we really need, software that does reasonable simulations to make better recommendations as to which experiment works best. And then some conclusions you can read. I really didn't say anything about the methyl-Trosi experiments. There are methyl-Trosi experiments for doing CPMG type experiments, but not for doing R1 row type experiments. So the methyl-Trosi experiments work for very large proteins. Lewis has done these on like half megadalton complexes. But the time scale is a little more restricted because there isn't an R1 row version that would get to higher strength fields. Well, I was hoping to do some problems today.